This section goes through some of the common radio architectures for point-to-point systems. This diagram shows a general depiction of a microwave radio signal chain and control path. On the transmit side, it consists of dual baseband IQ high-speed digital-to-analog converters whose outputs enter a quadrature modulator. This output then goes into a block-up converter that performs a single sideband up conversion up to the microwave frequency output. This microwave signal then gets amplified by a power amplifier and sent through the microwave antenna to be broadcasted over the air. For the receive path, the signal chain follows a similar reverse path of the transmit side. The microwave signal is received by the antenna, filtered, and then block down converted by an image reject mixer to a lower frequency. The signal then passes through a variable gain stage and is again mixed down to a lower frequency. At this point, some channel filtering and additional amplification is done prior to being digitized by the high-speed analog-to-digital converter for digital signal processing in the modem. Often, these systems will also have a DPD or digital pre-distortion algorithm to reduce or remove distortions in the transmitted signal caused by running the power amplifier close to saturation. These corrections are needed to improve system performance and to prevent adjacent channel interference. This DPD path taps the output of the power amplifier and routes a copy of the transmitted signal back to the transmitter's processing unit through a receive chain that is sometimes called an observation receiver. The received transmission can then be used to digitally pre-distort the signal being transmitted in order to correct for imperfections in the transmit path and improve the overall transmit signal chain performance. The full system shown in this diagram is sometimes broken up into different equipment pieces in different operator systems, as we will see in the next few slides. For legacy band, some systems are split between an indoor unit and an outdoor unit. The typical partitioning between the indoor and outdoor units are at the data converters and radio boundary. The outdoor unit, or ODU, for a legacy band includes the antenna through the amplifiers, up-down converters, and RF mixers, where the data is at baseband frequencies, typically around 350 MHz for transmit and 140 MHz for the receive path. This IF data will then go into the indoor unit, or IDU, through a coaxial cable connection. With the recent acquisition of Hittite Microwave and the previous Analog Devices RF and microwave product portfolio, Analog Devices can now cover the entire 6 to 44 GHz point-to-point legacy spectrum across the entire split outdoor unit. We have a wide variety of narrowband and high integration parts that span the full frequency range for microwave point-to-point systems. These products include power amplifiers, VGAs, microwave up-down converters, and microwave PLLs with integrated VCO functions for high-performance LO generation, as well as RF-IF up-down converters. The indoor unit consists of some amplifiers that pre- or post-condition the signal, and the data converters, along with the modem, FPGA, or ASIC. Analog Devices, as the world leader in data converters, has a wide variety of converters that can support each of the needed channel bandwidth in point-to-point systems. Some of them are shown in the slide. You can see that ADI has converters that support the LVDS data interface, as well as the newer JESD 204B high-speed serial interface. In this IDU, the data converters in the transmitter generally directly generate an IF signal using the on-chip NCO and digital modulator. Similarly, the converter in the receiver uses on-chip digital down conversion to shift the received signal to baseband for demodulation in the ASIC or FPGA. In a full outdoor unit system, the data converters reside in the outdoor unit, with the digital ASIC in an indoor unit and baseband data being passed between them up the pole. Analog Devices has produced the 809993 mixed signal front end, or MXFE, specifically to support such a system. The high-performance 809993 integrates two 14-bit 500 megasample per second DACs, along with four 14-bit 250 megasample per second ADCs to provide the needed converters for a full ODU radio, including the option for an observation path not shown in this diagram. The highly integrated MXFE provides these data converter functions in a single package, reducing overall board space and enabling smaller footprints for the ODU. You can see that these converters connect to modulators or demodulators that directly up or down convert to and from the desired microwave frequency band, reducing radio complexity by removing all stages of intermediate frequency conversion. This makes for a smaller radio with lower overall size and weight, ideal for a wide variety of installation types. This view of the same full ODU system shows an option for a digital predistortion observation path. The second pair of 14-bit 250 megasample per second ADCs on the 89993 is used for the observation receive path. We also show an optional parts list for using discrete converters to implement the same radio. Depending on the performance requirements and whether zero IF or complex IF modulation is chosen, the integrated 89993 MXFE or the discrete converters may be the better choice. Analog devices converter solutions support both approaches. In the case of the discrete converters, the sample rates must be higher to support a conversion to reject the sideband on the transmitter or the image at the receiver. This is the place that gigasample per second converters from ADI will fill the required needs well. Here we show a V-band full outdoor unit. With 7 gigahertz of allocation, there is plenty of bandwidth available for use, and so wideband gigasample per second converters can be used. In the case of a single 50 megahertz channel, it's more appropriate for the lower frequency converters on the previous slides to be considered. If several channels will be aggregated or several separate channels transmitted at the same time, wideband converters may be more appropriate. Therefore, a selection of 1 gigasample per second ADCs and the AD9625 2.5 gigasample per second RF ADC are shown for the receiver, with the dual 2.8 gigasample per second AD9136 shown for the transmitter. The radio configuration is direct conversion, with baseband data driving the microwave modulator and the quadrature demodulator driving into the wideband ADCs. In this example of a single conversion radio for E-band, the same converters are used. The AD9136 drives a quadrature modulator, which outputs a signal at an appropriate RF frequency, and then an image reject up converter is used to shift the signal to E-band frequencies in the 70 and 80 gigahertz bands. On the receive side, an image reject mixer is used to downconvert the signal to an appropriate RF frequency, where channel filtering can be done along with some amplification of the signal, after which the signal is demodulated or downconverted to the baseband frequency range, where the ADCs can digitize it and send it to the digital ASIC for signal processing by the modem. Here is an E-band direct conversion radio with a very similar architecture to the V-band radio shown previously. In this case, with the wide channels in E-band, the same wideband converters in the V-band radio can be used in the E-band radio. The flexibility of the same gigasample per second converters being able to support multiple different microwave system architectures make them a valuable and versatile choice when designing a new backhaul system.